So in the second part, we'll see what is KVL. KVL means that is short form for Kirchhoff's voltage law. Before going to the actual description of this Kirchhoff's voltage law, I will say some important points on which are required to be known before we apply this law. So first thing is we'll see what do we mean by traversing a loop. Okay, for example, if you have this circuit here, so in this circuit, if you see in this circuit, if you see there is a voltage source here. So this is the voltage source. Then you have three, say, resistances. Let's say this is 10 ohms. Two resistances. This is 10 ohms, and this is, say, 15 ohms, or this is also 10 ohm. Okay, 10 ohm and 10 ohm resistances are there. And when you in any form, when there is a completion of circuit, that means there is a loop over here, then we say that there is a completion of circuit, or there is a loop, and then we can traverse that loop. Okay, so you cannot ever traverse something when you don't have a loop in this case. Okay, so for example, if you have some circuit only like this, something like this and like this, then this is no more a loop, so there is nothing like a loop over here. Okay, it is something which doesn't form loop. So whenever you have a loop, then there is a concept of traversing a loop. What do we mean by traversing a loop here? Traversing is in a loop is we start from, say, one point, say this point O, then we go to point A over here, point A, then from A to B, then B to C, and we come back to A. So that is saying where we have traversed the loop, and we go on noting what is the voltages, and accordingly we go on adding those voltages, in algebraic sense, of course. So we go on adding those voltages one after the other till we reach the same point once again. That is traversing a loop. So for example, if I start from here, this is, say, 0 volts. Okay, O is 0 volts. Then when I reach here at point from O to A, when I reach from O to A, you see there is a 5-volt source, and the voltage here is increased by 5 volts. Okay, so we say that when I go from 0 to A, then the voltage is increasing by 5 volts. So 5-volt rise happens. So this is 5-volt rise happens. And when I go from A to B, then there is if you see this sign here, plus and minus. Okay, so we are going from plus sign to a minus sign. Please remember, here there was a rise because we went from minus sign to plus sign. Okay, minus was 0 and plus was 5 volts. So when we did that way, we got 5-volt rise. Similarly, when I go from A to B, then I say there is a drop of 2.5 volts, or whatever it is, there is a drop of voltage, say V10 ohm. Okay, drop of this voltage is V10 ohm. Okay, similarly, when I go again from B to O, so this point is O itself, this whole point is O. Again from B to O, again I go from positive to negative, and I say there is a drop. There is a drop from B to O. Okay, so 0 to A to B, and B to O. So if you see, if I come from A to B, there was drop of 2.5, and when I come from B to 0, there is again a drop of 2.5, and at 0 it should again become, this value should come out, same value would come. Okay, so if I take this traverse, then I write it as I am summing the voltage over a loop. summation of V over a loop, and I consider that particular sign also. So if you see, this is 5 volt, so from 0 to A is 5, then it is a drop, therefore it is minus V10 ohm, so this is minus V10 ohm, then it is again a drop of minus V10 ohm, and since we will always reach back to the same point, that would come to be 0. So this is a kind of concept of Kirchhoff's voltage law, that is sum of voltages in a circuit would be 0. Of course, you have to take in consideration the algebraic signs or the signs of those voltages. Okay, so if it is increasing, then you use positive. Okay, if it is decreasing, going from plus to minus, then it is negative, and again it is negative here. So depending on the sign, you go on adding those voltages, and finally since you reach the same point, that is, if you started from 0, you will reach the same point at 0, and therefore the total of the voltages in a circuit or in a loop would come out to be 0. So for the sake of further explaining the things, I am taking slightly complicated circuit here, so that I can explain the Kirchhoff's voltage law here. So if you see here in this circuit, there is a voltage source over here, then there is some component, I am not giving the name of that component, that is here, then another component 4 here, and another component 8 here. Okay, this is 8, and another component 9 over here. Okay, and let's say this is loop number 1. So if you see how many loops are there in this, if you see, there are 2 loops. One is the loop, this loop, it is completing a circuit, so this is one loop over here. Okay, and there is another loop over here. So just to name them, this is loop number 1, so this is loop 1, and this is loop 2, and we'll try to write Kirchhoff's voltage law for that particular loop, or try to traverse that particular loop. So let's say loop number 1 we are trying to traverse. What I do here is, for each of them I just put a this signs could be put arbitrarily. Okay, so you could put plus, minus, minus, plus. So all these components you can put all the signs arbitrarily. If you see here, I have deliberately drawn this part. This part doesn't form any loop. Okay, so we don't say anything about Kirchhoff's voltage law for this. So now let us try to write KVL for loop 1, which is this one. Okay, KVL for loop 1. So if I start from here, you can see this is V1. Okay, V1, if you start from this point, so first thing is, for loop 1 there is rise of V1, so V1 plus with a plus sign. Then I go from here to here, this is V3, and going from plus to minus, therefore this is a drop in voltage, so that's why it comes with a minus sign, minus V3. Then I have given a sign over here. This all signs I have given from myself, that is arbitrarily I have given. So this is minus and plus, so again it is giving a rise. Okay, minus to plus is rise, so it comes with a positive sign, plus V4. Then here minus to plus, if you see here, minus to plus, it is negative with a negative sign. Then again it is minus to plus, it is with a positive sign, increase. Okay, what you call the potential is increasing. Okay, similarly here also from minus to plus, again the potential is increasing, so plus voltage. So if it is increasing, that is, if you are traversing from minus to plus, it is increasing, and then you call it as increase in rise in potential. And if it is when you are traversing and it comes from plus to minus, or coming from plus to minus, then it is called drop in voltage. Okay, and it comes with a negative sign. So this is for the loop 1. Similarly, you can try this with loop 2. Okay, so for loop 2, if you see, I am traversing from here to here, loop 2. So first is V2, again V2 is positive, then V6 minus to plus, again minus to plus, again increase V6, then plus to minus, so it is minus V7, drop, again plus to minus, it is again a drop, so with a negative sign, minus V4, and here again minus to plus, it is a increase, so rise, plus V3. So that is how we traverse the loop and write the voltages in that particular loop. Okay. Now let us take what do we mean. There is certain convention in a element. So let's take a simple element, that is, suppose you have a resistance over here, a resistance is shown over here, and what by Ohm's law, if you see that the voltage across the resistance is taken as I1 into R1. Okay, this is the amount of voltage, and when there is a drop in this particular resistance, okay, you say that the voltage across this resistance is I1 into R1, and you mean that the tail of the current is positive and the head here is negative. So if the current is going in this direction as shown, okay, then this part would be positive and this part would be negative. Okay, so this equations comes by that way. V1 is equal to I1 into R1. Similarly, if I have this condition, that is current is going like this, okay, and this is R1, and if I put this as a negative sign and this as a positive sign, then I say that this has against this sign convention, and therefore V1 is minus I1 into R1. So this is a convention taken in a resistance. Okay, the tail of the current will be positive and negative, that is the normal convention, and anything changes from this, it becomes a negative convention, that is minus sign. Now let's see what do we mean by Kirchhoff's law. We have already been seeing that. So here Kirchhoff's voltage law, the amount of voltage rise and amount of voltage drop around a loop totals to 0. That is the equations we were writing so far. We'll consider that how it is applied to a network in the following circuit, the circuit that comes up. While applying, we must consider the voltages of the component in that loop only. Okay, so don't consider voltage from another loop, that we have seen. That is why I was trying to tell what do we mean when we traverse a loop. The sign of the voltages and the components, whether they make voltage rise or make voltage drop, that has to be taken care of. So that is how you apply Kirchhoff's voltage law. So let us see, for example, this problem, simpler one, which we already did. Here we'll do it again, now with the familiarity of that law. So now I am traversing this loop. Okay, so I start from here, so this is minus to plus, it is 5 volts. Okay, increase or rise, whatever we say. Then plus to minus I have given, so minus V5, drop here, and then this is, I have put minus to plus. So if you see by this convention, I should write it as a rise. Okay, so these are the three things here. So now I write it as 5, that is rise, minus V5 is drop, and plus V10, because I have given the sign like this. Okay, going from minus to plus, and this should be totaling to 0. Now if I remember the sign convention, I must write V5, because V5 is like this. This is 5 ohms, and I have taken this as plus and this is minus, this is V5, and the current is in this direction, I1. So I write V5 is equal to I1 into 5. Okay, if you remember this convention we have just seen on the previous page. Similarly, if I write for the second one, that is, this is V10, this is 10 ohm, what I have seen is this minus, this is plus, and the direction of current is like this. And my convention says that V10 should be written according to this convention as I1 into 10 with a negative sign. Okay, because it is, the tail comes here towards the minus sign, which is against that particular convention which we take. So when we put this into equation, you get this. This is a very familiar equation, and you can calculate value of I. So this was a very simple circuit which illustrates that how you can use KVL to find the current in this circuit given the voltages and the values of the resistances. Now let us move on to slightly complicated circuit here. Okay. In this circuit we'll see how to write the loop equation. So if you see here, there are 3 loops, I1, I2 and I3, and these 3 loops will try to write the equations one by one. If you see, I have given the signs. These signs are put arbitrarily by me. I have defined those signs. Okay, voltage, the resistances are given to us, and I have put that sign. And this 12 volt actually I'll write at V12. This 2 volt I'll write V2, V4, V6 and V20. That is convention I am using. So whatever is the resistance value, that is my voltage value. So let me write for the first loop. For the first loop, if you see, there is, if you start from here, the direction is given, direction of I1 is given. So first thing, there is a rise 20 volts. Okay, then this is according to this convention, this is minus and plus, then there is a drop, minus V12, and here minus 2 plus. So this is, sorry, plus to minus, again this is plus and minus, again this is a drop, so minus V2. So this is my first equation for the loop number 1. And I can use the values of V12 is 12 times I1. Please remember the convention. Okay, plus to minus, the current is flowing. And second one is again from plus to minus, I1 is flowing. Okay, and I2 is flowing. The total current flowing from plus to minus is I1 minus I2. Okay, so I1 is taken plus positive because I am taking that as convention. So I1 minus I2 is the current flowing in that direction, and becomes 2 is the resistance. So V2 is this much, and I can put that into the equation to get this equation. Okay, so 12 minus and 2 I1 minus I2, and that should equal to 0. So that is my Kirchhoff's KVL equation, or you can say mesh equations or a loop equation for this particular loop I1. Similarly, you can write this loop equation for I2 in a similar fashion. So according to I2, if you see the direction of I2, this V2 for this appears at from minus to plus. So V2 is rise here, V2 is rise in the voltage, so V2, then minus V4, there is a drop, and then again minus V6 is again a drop, which equals to 0. And then again I'll see V2 is going from, if you see this V2, if I want to take the convention for V2, my current is going from, I2 is going from, if you want to write V2 by using the convention, V2 should be equal to the current flowing into it. So current flowing into it, this I2 minus I1. I'm taking I1 and I2 as a reference. So if I take I2 as a reference, then I should take, it is going, the tail is towards the negative sign, so I should take minus sign and the resistance. So this is I2 minus I1 into 2 is V2. Okay, and if you include that sign, this is what you get, I1 minus I2. Okay, in a similar way you can find the next one, 4 times I2, only I2 flows into it, and it goes from plus to minus, so it is a drop. And similarly here also it is a drop. And when you apply this, you get this as a second equation. Similarly, the third equation you can calculate by yourself. V6 is rise, V20 is fall, plus to minus, and 40 volt is plus to minus, it is again a fall. Okay, so that is how you write this equation, and then you put the values according to that. So here if you see V6, if I want to calculate, I take I3 as a reference, because I am writing from for I3, then I take I3 as a reference, and since it is taking, the head is towards the negative sign, therefore I'll have to take minus, and the total current is I3 minus I2, okay, into 6, and that is what is here. Okay, I3 minus I2, this is I2 minus I3, taking negative sign into that. So that is how you take this as the third equation. So these are the three equations in I1, I2 and I3, and once you know this, you can write these equations in this way. All the three equations just put together, same equations. And if you see these equations closely, you will find that I can write this equation in a matrix form. Okay, so I1, I2, 3, I1, I2 and I3 are three currents which are written as a as a column vector here, and then there is a matrix of resistances, or you can say impedance is Z, and these are the voltages taken together, that is here. So same thing written in a matrix notation. And in general, you can write any such circuit into a matrix notation. There will be some matrix Z, okay, there will be some currents I1, I2 up to IN, and there would be some voltages in the loop. So these are loop matrices. This is called incidence matrix or Z matrix. This is called current matrix. All the loop currents are there. I1, I2, I3 are the loop currents. If you see, I1, I2 and I3 are the three loop currents, and these are the voltages in a loop. 20, 0 and 40 are the voltages in a loop. So if you see, they are 20, 40 and 0, no voltage source in this loop, so that is 0. So this is how you have. Now this, if you see, makes things slightly more procedural, because if when you write Zi into V for this particular type of circuit, I can devise a very interesting way of writing the equations. Okay, I can write this matrices straightforward by looking into the circuit. I don't need to actually write those equations and then come to write a matrix here. I can go other way around. I can write the matrices straight away by looking into the circuit. How do I do that? So we'll see how to write those equations in a matrix form just by inspecting the circuit. Okay, so let me first explain you the rules around it. So if I say it is Zii, so if an element here is Zii, that is one of these elements which will come over here. So Zii will be one of these elements. So it would be sum of resistance in loop I. So all the resistance, if I sum up in a particular loop I get Zii. Okay. Then these are diagonal values. Then there is a Zij. Okay, Zij and Zji would always be equal. They are same. Okay, if you want to see here, you can just check. This value and this value are same. This value and this value are same. Zji and Zij are always going to be same. But how do I calculate that? So Zij is sum of resistance common to loop I and J. So if I take two loops, whatever is the common resistances between them, that becomes sum of those resistances will become Zij, and that will be same as Zji, and it will come with a positive sign if the currents I and J, the two currents, are in the same direction. So if the two currents are in the same direction, then it becomes come with a positive sign. That addition comes with a positive sign, and it comes with a negative sign if the current I and J are in opposition to each other. Okay, so these are the two things. One are the diagonal values, other are the off diagonal values. So if you calculate those two, your Zij is complete. Then this current is the loop current. So I1, I2, this is very straightforward. Number of loops will give you the loop currents in each one of them. Vi, or the loop voltages, can be calculated as sum of voltages in loop I considering their signs. So if they are adding together, they add up together. If they are cancelling each other, subtracting each other, then you get with a subtraction sign. We'll come to that. First, let us try to see with this circuit itself that how do we calculate the values of Zij, the impedance matrix of Z. So if you see here in this circuit, there are three loop currents. That means that I have to write three equations. So I can write I as straightforward, I as three loop currents, I1, I2 and I3. If I is defined once, then Z is also defined because it will be multiplied. Therefore, this is going to be a 3 by 3 matrix. Okay, so depending on how many loop currents are there, you can define the impedance matrix to that. And once the impedance matrix is defined, then you can start calculating the values. So first thing is, we'll try to see how to calculate the diagonal values. Let's say Z11. If I want to calculate Z11, I go to loop 1. Okay, I go to loop 1, which is this one. Okay, I1, and in this loop I see what is the total sum of resistances. Okay, what is the total sum of resistances here? If you see, this is 12. In loop 1 only two resistance come, 12 and 2, and total sum is 12 plus 2, which is 14. Now let us calculate Z22. So I go to loop 2, this is loop 2, and see what is the total set of total resistances. So if you see, there are three resistances in this, that is 2 ohms, 4 ohms and 6 ohms, and total sum of those three is 2 plus 4 plus 6, that is 12. Similarly, I can calculate third one. So third one is, how many resistances are there? There are only two resistances in the third loop, that is 6 plus 20, and that comes out. So I have calculated the three diagonal values, Z11 and Z22. It's as simple as that. Now let us come to off diagonal value. If I want to calculate Z12, which obviously would be equal to Z21, okay, and that I do, I'll go to loop 1 and 2. Okay, I'll see 1 and 2 together. Okay, so loop 1 is this and loop 2 is this. So in these two loops, what is the common element which is common to these two loops? The common element is only one in these two loops, that is these 2 ohms. This 2 ohms is common between these two loops, and that will come as Z12. So I know the value of this is 2, but should it be plus 2 or minus 2? That will be defined by the directions of the currents I1 and I2. So if you see, in this 2 ohm, I1 is flowing in this direction. Okay, in this 2 ohm, I1 is flowing in this direction and I2 is flowing in this direction. So these two currents are in opposition to each other, therefore it will come as a with a negative sign. If these two would have been in the same direction, I1 and I2 would have been something like this. This was 2 ohms, and I1 would have been like this, and I2 also would have been like this. Then it would come with a positive sign. So if they are in opposition to each other, it comes with a negative sign. If they are not in opposition but they are in same direction, then it comes with a positive sign. So here Z12 comes out to be -2. Now we'll go to Z23. So I'll see 2 and 3 together, and this is the common resistance between 2 and 3. And if you again see the directions of I1 and I3, they are opposition to each other, so it becomes -6. Now if I see Z13, 1 is here and 3 is here, nothing is common between them. So there is no common resistance between them, and that is what I say that there is no common resistance, means I will take it as 0. So Z13 and Z31 are 0. So utilizing these values, I can now see, I can find the values of Z1, Z2 and Z3. Now what about the voltages? So V1, V2 and 3 loops, so there will be 3 voltages. So for calculating V1, that is voltage in loop 1, what I do is I see this loop number 1, I see this loop number 1, and I calculate what is the total voltage in loop 1. Okay, if you see, the total voltage in loop 1 will be 20 volts, and according to current I1, it is giving a rise of voltage or drop of voltage. So if you see, according to traversal direction of I1 is in this direction, so it is rise. So it comes out as 20 volt with a positive sign. In V2, you just see only V2. Just see the loop 2. In loop 2, if you see, there are no voltage sources in loop 2. So no voltage sources, so V2 will be equal to 0. In V3 there is one source, and if you see, the total here is 40 volts, and depending on the direction of I3, it is going from this direction to this direction, that is from positive to negative, so it comes out to be -40. So that is how you can, now you have V1, V2 and V3, you know I1, I2, I3, there are knowns here, and you know these values of Z. And you can use these values to write the matrix equation straightforward. If you see, while calculating all this, I have not resorted to any kind of equations. I have just seen from the circuit, and if you see, I think they both match. Okay, they both match. And this method, of course, there is some limitation. This will match, but this may fail when you have current sources also. So this, I have used this method of writing when you have only voltage sources in this circuit. All these are voltage sources. There are no current sources in this. But if the current sources are there, then also you'll have to first convert those current sources into voltage sources. Then you can again write it. All of them are in voltage sources. So this is how you can write this equation. If those current sources are not convertible into voltage sources, then this method won't work. But normally, in all practical situations, current sources and voltage sources are interconvertible because they are practical sources. So you can always use this method of writing these equations for this kind of circuits. So this is, if you see, they are same, and if you have a mathematical software, you can find I1, I2 and I3 by simply inverting this and I1, I2, I3 and multiplying this with this. So inverse of this, put it over here, and you will get the values of I1, I2 and I3. Or you can solve the equation, they are one of the same things. So I'll stop here for